Okay, so today we're going to be covering function theory, which is probably the first topic in these review sessions that's really going to be more challenging. What we did yesterday, the lines and quadratics, it's really foundational material. Today we're going to get into some of the meat of the exam. So we're going to go over really just the properties of functions today. We're not going to talk about exponential functions or function transformations or anything like that. We're going to talk about domains and range of functions, what a function is, how to graph a function, and how to interpret its graph. We're going to talk about composing functions and inversing functions. And then we're going to solve some problems that are accessible to everyone in SL and HL. Then for the higher level students, we're going to talk about even and odd functions and also the specific conditions under which an inverse exists, including possibly with restrictions. And finally, we're going to do a couple of higher level problems that are getting pretty difficult. So let's get started with something very, very basic. What is a function, and how do I differentiate a function from some general equation? So a function is essentially a rule that assigns one number in its domain to one number in its range. So critically, that means that a function has to have the same output for any given input. And if you think about that graphically, it means that the function is going to pass the vertical line test, which is why, for example, a relation like x squared plus y squared equals 1 is not a function, because if I isolate y and square root both sides, I find y equals plus or minus 1 minus x squared. And that gives me two possible values for each x. So a function is a completely deterministic rule. And if you don't have a relationship that is deterministic in that way, if each x does not precisely go to one y, then you don't have a function. So this is also pretty basic, but we can evaluate functions by simply plugging in the value that we care about into the expression that we're given. So if I'm told that f of x is 3 minus x squared, then to find f of 3, I just plug in 3. And in this case, I would get -6. So I'm going to give you guys 30 seconds to a minute to try this exercise, and then we're going to go over the solution together. Okay, let's go over this. So I have f of x is 5x minus 3, and I know that f of a minus 3 is equal to 2. So the easiest way to do this is to just evaluate f of a minus 3 is going to be 5 times, and I'm replacing x with a minus 3 in the expression for my function. So 5a minus 3, and then minus 3 again. So this becomes 5a minus 15 minus another 3 is minus 18, and that is all equal to 2. And that means that 5a is equal to 20, and a is therefore equal to 4. So that's my answer. All right, next slide. The domain of a function. So domain is the set of possible inputs that a function can be given. And we often talk about the natural or largest possible domain of a function, which is the set of all possible values that the expression of the function allows us to input. For example, if I have the function square root of x, I can't put in any negative values because on the IB we deal strictly with real functions. So the natural or largest possible domain of f is x belongs to real numbers such that x is greater than or equal to 0. Now, we talk about the largest possible domain because for any function, you can arbitrarily restrict the domain. I can just say, for example, that the function g of x is equal to x squared is only defined for x greater than 0. And it doesn't mean that x squared is undefined for x greater than 0. It just means that I'm only defining g to exist for positive x. And this is going to be something that we're going to circle back to when we talk about inverse functions. So as a quick example, if I'm talking about the largest possible domain of f of x is equal to root 5 minus 2x, then I know that the radicand, the inside of the square root, cannot be negative, which means that 5 minus 2x is greater than or equal to 0. And if I rearrange for x, that means that x is less than or equal to 5 over 2. Okay. Range of a function, sort of a similar concept. This is the set of possible values that a function can output. So if I have the function f of x is equal to x squared plus 1, then since x squared is always going to be positive and I'm adding 1 to that, the range of the function is f of x greater than or equal to 1. So the smallest value the function can take is 1, and it can take any value larger than 1. And sometimes if the domain of a function is restricted, the range might also need to be restricted as a consequence. So if I have a function defined by 2x plus 1, but I'm restricting it to be defined only between x negative 1 and 1, not inclusive, then the range of f of x is only going to be from -1 to 3. And I found that by plugging in -1 into 2x plus 1. That gives me -1 as the lower bound. And I plug in 1 into 2x plus 1 to find the upper bound of 3. Now, when we're talking about domain and range and we're answering questions about domain and range, it's useful to have a standardized notation for representing intervals. And that's mostly because oftentimes we have kind of messy inequalities. We have inclusive on one end, exclusive on the other. Sometimes you have multiple ranges for the domain. And the way we end up writing this, most typically, is using this kind of bracket notation. So I would say, for example, if I had a domain of x greater than -1 and less than or equal to 5, I could either write it in this set notation that you should be sort of familiar with, where the little symbol here means an element of, and r is real numbers. I can also use the interval notation. So I can say x belongs to, and this is an interval, starting at -1, going up to 5. And the circular bracket, the regular brace, means that that end of the interval is not inclusive, right? So that corresponds to -1 less than x. And the square bracket means that that end is inclusive. So if I have x less than or equal to 5, I put a square bracket. And you can also visualize this on a number line, right? I can draw from -1 to 5, and I just put a hollow point at -1 because it's not inclusive, and I put a solid point at 5 because it is inclusive, okay? Again, at any point, if you guys have questions, drop them in the chat, and we'll do our best to respond to those. So now, another chance for a quick exercise. I want you to find the domain and the range. Okay, so let's get started with part A. We're thinking about the domain of a function which is under a square root, or has a square root in it, which means that the term under the square root cannot be negative. So 16 minus 2x squared has to be greater than or equal to 0. And if I rearrange this, that means that 16 is greater than or equal to 2x squared, or x is less than or equal to, x squared is less than or equal to 8. And when I square root both sides of an inequality like this, I have to remember that if I take a negative number squared that's smaller than the square root of 8, it's going to become a positive number smaller than 8. So this means that my actual interval for x is x less than or equal to the negative square root of 8, and greater than or equal to negative square root of 8, and less than or equal to the square root of 8. And just being very careful, we notice that these are inclusive inequalities, which means I need square brackets, so that makes it option 4. All right, and I'm going to erase this, and then we'll do part B. So now we're thinking about the range of f of x. And f of x is a square root, which means that I can never get a negative number, so I know at least that I'm dealing just with a positive range. And I also know that because x squared is a positive number, and I'm doing x16 minus twice x squared, the maximum value that the term inside the square root can take is 16. So it's going to be 16 when x is 0, and then as x gets bigger than or smaller than 0, it's going to drop off. So the maximum value inside the square root is 16. If I square root that, it means the maximum value of f is going to be 4. And the minimum value is just going to be 0, because if I do 16 minus, for example, the endpoint of the domain we found, root 8, I'm going to get 16 minus twice root 8 squared is going to give me square root 0. So the option is going to be number 3. So let me maybe explain this a bit better. If I were to plot just the inside of the square root for a second, I'm going to have a maximum at 16, and then I'm going to have a concave down parabola, and then these values here are root 8 and negative root 8. And I know that the function doesn't continue outside of that interval because we said that the domain was between, and I don't know why I put the negative inside the square root there. That's not allowed. Negative root 8. That's the domain of the function, right? So the range of the radicand, the part that's inside, is from 0 to 16. And if I have numbers between 0 and 16, let's say I have the numbers 0, 1, 4, 9, and 16, right? These are just some numbers that are, some integers that are going to be in my domain. And I have all the numbers between them as well. If I square root each of these, I'm going to get 0, 1, 2, 3, and 4. So by taking a square root, I'm essentially transforming the domain in a predictable way. I know that I'm not going to change the sign of the domain, and I'm not really going to move things around, all that's going to happen is every value that was in the range of 16 minus 2x squared is going to get square rooted. So my 16 becomes 4, something slightly beneath 16 becomes something slightly below 4, and that goes for every value between 0 and 4. Because if I take the square root of any real number between 0 and 16, it's going to be between 0 and 4. Okay. So one sort of common pattern that shows up on exam problems is to use functions as a model. And this is super common in SL, but also quite common in HL problems. Basically, we're using a function to represent some real world scenario. And you're going to have the output variable typically is going to take on a letter that represents some meaning. So in this example that I have on the screen, I have h for the height in kilometers, and I'm giving it as a function of t, of time. And you have to be careful with these problems to think about what the units of in the question are. You have to be very careful to include the units in any answers that you provide. And you also have to be careful to think about the way that the question is going to be stated to you is often to tell you something about the real world that you have to translate into kind of functional notation. So for example, if I have a rocket that whose height after t minutes is given by the quadratic function negative t minus 4 squared plus 9, then you might be asked, for example, about the maximum height of the rocket, which is going to happen because this is a concave down parabola when t is equal to 4. Let's try an example problem. So I'm going to give you maybe 4 minutes to get started on this, and then we're going to go over it. Okay, I think we're going to go over part A at least. So the height in h kilometers of a rocket ship t minutes after midday is h of t is equal to negative t minus 20 squared plus 16. So state the time at which the rocket reaches its maximum height. Right, so again, I have a concave down parabola in negative t minus 20 squared plus 16. I'm in vertex height form, so finding the vertex is actually very easy. The time at which I reach the vertex is when the term inside the square root is 0, so t minus 20 is equal to 0, so t is equal to 20. Now the question is asking us to write it in the format HHMM as a time of day, so it's just going to be 12:20. And similarly for part AII, because it's in vertex height form, I know that the y-coordinate of the vertex is just this plus k term, so it's going to be 16 kilometers is the maximum height. So let's check the MCQ answers. 12:20 and 16 kilometers. Okay. And then part B, find the time at which the rocket takes off. So the rocket takes off from a height of 0. We're assuming it leaves Earth. So h of t is equal to 0. And that's also the condition under which the rocket returns to Earth. When it comes back down, the height is also 0, which means that negative t minus 20 squared plus 16 is equal to 0. Or in other words, t minus 20 squared is equal to 16, which makes plus or minus t minus 20 equal to 4. And sorry, the plus or minus should be on the other side. Plus or minus 4. So then I'm going to have either t is equal to t, yeah. So then I add 20 to both sides, and I have t is equal to 20 plus 4 or 20 minus 4. So that's 24 or 16. Now, we're going to assume that the rocket took off before it landed. That's probably a reasonable thing to do. And we're going to report the answers in the same format as we did in AI. So take off at 12:16 and land at 12:24. So it's in the air for 8 minutes. Let's see the options. Take off at 12:16, return at 12:24. Perfect. Okay. So function graphs. I'm moving on to a new topic here. So the graph of a function is a visual representation of all the points x comma f of x on the function. So if I take all of the inputs and all of the outputs and I plot them on a coordinate plane with the outputs on the y, I'm going to get the graph of a function. Now, most of the functions that you deal with in IB, because they're sort of continuous elementary functions, you're going to have infinitely many points that lie in the domain and infinitely many points in the range. And so you're going to usually end up with graphs that look like straight lines. And in this little animation, you can see how the straight line of a function is actually nothing more than infinitely many points kind of blending together. So you start with a small number of points, and as you increase the number of points, you essentially have a line. So we can also find the value of a function at a specific value by reading from the graph. So if we know that the input-output is an xy coordinate, then we can, if we're given the input to a function, let's say we're given a, all we have to do is look on the x-axis for the value of a and then look up to where the y value that the function takes at that point. So in this case, if I was looking for f of 2 is equal to 3, I go to the x-coordinate of 2 because that's my input, and the y-coordinate is 3. That's my output. F of 2 is equal to 3. So here's a quick example for you guys to try on your own. Okay, let's go over this. So f of minus 3, remember, minus 3 is the input to the function. That's the x-coordinate. So I'm going to go to minus 3 on the x-axis, and I'm going to look for the y value at that point, and I find 1. So f of minus 3 is equal to 1. Now, for a I am looking for f of 0. So that's just x-coordinate of 0, which is right there. And I look, and I find f of 0 is equal to 3. Now, B is a little bit harder because we're working backwards, but essentially, I know that f of k is equal to minus 1. So the output of the function is minus 1, and the output is the y-coordinate. So essentially, I have a horizontal line at minus 1, and I'm looking to see where it intercepts the function. And that's going to be at negative 4, at the x-coordinate of negative 4. So let's put that in. So graphing with technology. Your calculator can basically graph any function. And what it's doing under the hood is it's essentially graphing individual points that are very close together and connecting them with straight lines. And that's what you're seeing on your calculator. That's why it looks a little bit grainy. And that's why your calculator has settings for step size, among other things. But when you actually use your other calculator's features to find either intersections or maxima, the calculator is going to use even more precise systems for finding high precision answers. So you don't need to worry about the step size making your answer slightly wrong. One thing that your calculator can do is help you find the x-intercepts of a function. So on a TI-84, you have a 0 function once you've graphed something, and all the calculators have something similar. I'm just not 100% sure what the keys would be. But for example, if I had a function or a curve, y is equal to x cubed minus 3, and I plot it on the calculator, I can find the root even though I don't have an algebraic way of solving the equation x cubed minus 3 is equal to 0. Okay. Similarly, we can find the y-intercept of a function. This you can sometimes do just by hand if the function is not too bad. Remember, the y-intercept is where x is equal to 0 because it's the vertical line that goes through x is equal to 0. That's the y-axis. So if I plug in x is equal to 0 into my function, I can find the y-intercept. In this case, the 3x squared is 0, and the minus 3x is 0, so I just have root 4 over root 9 is 2 over 3. If you can't do this by hand, if the numbers are just too messy and it just doesn't work out, after you've graphed a function on your calculator, you'll have a setting or a feature to find the value of the function at a specific x value in the domain. And you have to make sure that it's inside the window that you've graphed, and we'll see an example of that in a second, but just bear in mind that you can do that also for y-intercepts. So I'm going to give you a second to try this question. I want you to find the x-intercepts and the value of the function at 3. Okay, so I have the function x to the 7 plus 6x divided by 5x times x minus s times x plus 1. So I'm going to go to my y equals to enter the function, and I'm going to start by putting in a square root. And I prefer to go actually to math and frac and put in a full-size fraction. It stops me from making the silly error of multiplying instead of dividing, because it means you have fewer brackets to take care of. So now I write x to the power of 7 plus 6x, that's in the numerator, and then 5x times the x plus 1. I'm going to put a minus 1 outside like that. All right. Now, before I graph, I'm just going to set my window. I usually do minus 10 to 10 for both x and y, at least as a starting point, and then we can kind of go from there. So let's graph this. All right, so it looks like I might have to zoom in a little bit. I want to keep x equals 3 in my domain because I'm going to need that for part B, but I'm definitely going to zoom in on the roots near 0. So I'm going to go from -1, say, to maybe 4. Oh, that didn't work. From -1. Oh, I have to use this negative. That's why. -1. Yeah, maybe it's worth making a note of that. On your calculator, if you want to type a negative number, you cannot use the minus symbol. You have to use the negative symbol. I don't know why they decided to make those separate, but negative means subtraction, which means you have to subtract from something. If I just put minus with nothing in front of it, the calculator is going to give me a syntax error. So I'm going to go from x -1 up to x 4, and that should be good for the y. I might do from -1 to 5 or something like that. Maybe 10 for this one. And now graph. All right, so it looks like I'm going to have 2 intercepts. I can find them by going to second and calc or trace to get to calc. And I can use my 0, which is option number 2. We can also just scroll down. And the calculator is going to ask you first for the left bound, which means you need to scroll to the left of the 0, hit enter, then scroll to the right of the first 0, hit enter again, and it's going to say guess. Guess just means, are you, do you have an idea of where the 0 is? Because if you can go close to the 0, the calculator is going to find it a bit faster. It's not super helpful, but sometimes on exams, if there's a really, really complicated function and you can see where the 0 is, you can spend less time waiting for the answer by using the guess. So enter. I find x is equal to 0.200 is the first one. So it's one of these two options. I just need to find the second 0 now. So I'm going to do the same thing again, go a little bit faster. Left bound here, right bound here, enter. And I find 1.335, which I'm going to round to 1.34. So it means I have option 3. So we had, for part A, I believe we had, yeah, it was 0.200 and 1.34. Now I'm going to try and set it up with the calculator in parallel for part B. Okay, so we were looking for the value of the function at 3. And the way to do that is just to go to second calc again, and we're going to go to the value option here, which is number 2. And I'm just going to type in, sorry, I must have hit the wrong option. Second calc, value, 3. Just enter that. And the calculator is going to scroll to that position exactly and tell me that the y is 5.06. Perfect, 5.06. All right. Moving on, intersections on the GDC. This is not too dissimilar to finding the roots, but your calculator also has an intersect function that allows you to find arbitrary intersections between functions. So this is really, really helpful when you have equations that you can't really solve algebraically, or you just don't want to solve algebraically and it's a paper 2, even if you could. You can just plot them on the calculator, and as long as the intersections are in the window, you'll be able to find their coordinates very precisely. So let's look at an example. I want you to find the coordinates of the intersections of y is equal to that whole thing and y is equal to x plus 1.2. So I'll give you 2 minutes for that. All right, so I'm going to type in the function that I have. I'm going to start by putting a fraction in. I'm going to add a square root. And I'm going to do 5x to the power of 5 plus 2 minus x. And that divided by x squared plus 1. And then all of that is supposed to be equal to, in the y2, x plus 1.2. All right, I'm going to also reset my window to kind of -10 to 10 for the moment, just so we have a good starting window and we can zoom in if we need to. Let's graph that. Okay, so it looks like we're going to need to zoom in kind of close to between -1 and 1. So let's do that. Let's do -1 and 1. And we'll do maybe -2 and 2 for y. All right, beautiful. And to find the intersections, I'm going to hit second. I'm going to hit trace to go to calc. And now I'm going to go to option number 5, intersect. And this time we don't need to do left bound, right bound. We just need to kind of go close to the intersection. It's going to say first curve. And this is because if you have 3 curves on the calculator, you can use the arrows to pan up and down between the calculator, between the different curves. In this case, there's just 2 curves. It doesn't really matter which 2 I pick. It's the intersection of this curve and this curve. And I find x is equal to -0.873 and y is equal to 0.327 if I round that to 3 sig figs. I'm going to do the second thing to find the second intersection. One more time, intersect. And the blue curve, red curve, and guess. And now I find 0.139 if I round that, and 0.134. So let's go back and enter that in as our answers. So we had 0.873 and 0.327, and the second one was 0.139 and 1.34. So that's option number 1. Perfect. Vertical asymptotes. So a vertical asymptote is a vertical line that a graph approaches but never actually touches or crosses. And in the case of vertical asymptotes, these occur because the value of the function blows up. It gets exponentially larger as it approaches a certain value, which means that the function becomes infinitely large or infinitely small, infinitely negative as you get close to certain values of x. And this can happen, typically because I have a function being divided by another function, and when the denominator is 0 or near 0, I know that I can't divide by 0, that's undefined, and any number divided by something close to 0 is going to be quite large. So you get a vertical asymptote when the denominator is 0 and the numerator is not 0. Because if I have x divided by x, then even though the function is undefined at 0, there's not going to be an asymptote because the x's will cancel. So as an example, if you were trying to find the equation of the vertical asymptote of 1 over x cubed minus x plus 1 on a calculator, what you would do is you would try and find when the denominator is 0, right? So you would plot that on the calculator like we did earlier, and you would try and find your 0. You would find x is equal to approximately -1.32. Horizontal asymptotes, similar concept, except now I have a horizontal line that the function is approaching, which means that as x gets very, very big, or it gets negative, like very, very negative, it's going to tend towards a certain value without ever reaching it. And this is kind of connected to limits, which we'll talk about in, I think, about 2 weeks' time. But for now, you can just think about the behavior of a function when you put in a very, very large x. So this example here asks me to find the equation of the horizontal asymptote of y is equal to √3x divided by root of x plus 1. And this is a calculator question because it's not a rational function that you can sort of find the asymptotes of by hand, but we will talk about that, I think, this week. So all you have to do is plot this on your calculator, and you just use the trace feature to essentially inspect what value the function approaches as x goes to infinity or to negative infinity. So you just kind of pan to the right or to the left. With that said, let's try an example. So I want you to find the vertical and the horizontal asymptote of this function I've given you. You're going to go to your functions panel where you enter these y's. Make sure you clear everything out that you have before. And now I'm entering a fraction again, a rational function. So I'm going to hit math, and I'm going to go to fraction to enter a fraction. We're going to put 3x cubed. Then we're going to put minus 5x plus 2. And that all gets divided by, that's x cubed minus x plus 1. And what I'm going to do, just to be able to find the vertical asymptote more easily, I'm actually going to also plot the denominator. So I'm going to plot on its own x cubed minus x plus 1. And while we're here, I think it's worth maybe showing you a pretty cool function on your calculator that comes in handy a lot in calculus, which is instead of retyping the entire thing in the denominator, I can actually go to vars and go y_vars function, and I can put, in this case, it was y2, and this will substitute the expression that I found there into the denominator of y1, okay? And I'm going to keep my sort of standard window. I'm going to go from -10 to 10, -10 to 10, and graph this. Okay, so what do we see? First of all, we're looking at the blue curve, right? That's the one that's actually the function, and the red is just the denominator. It's going to allow us to find the exact coordinate, the exact equation of the y asymptote. So I'm going to go to trace, and I'm just going to scroll to the right and see what happens to the value of my function as I get very large. So I'm getting to like 2.97, and if I keep going to the right, the calculator will extend, and I'm basically getting closer and closer to 3. So my horizontal asymptote is at x is equal to 3. And now to find the vertical asymptote, I want to go find the 0 of this red curve. I'm just going to zoom in quickly to show you how those two things correspond. You notice that the vertical asymptote of the blue curve is exactly where the red function crosses 0, all right, which is what I told you guys a second ago. It's because the denominator is 0 that I even have a vertical asymptote. But if I go to calc and I try and find the 0, right now I'm on the blue curve, and I'm interested in finding the 0 of the red curve. So I'm just going to arrow down to get to the red curve, go to the left of the 0, go to the right of the 0, and hit enter to find it. And I get -1.3247. So if I round that, -1.32. All right, so let's go back to the question. We should now have our answers. We found a vertical asymptote. That was the one that we just found, the -1.32. And the horizontal asymptote was at y is equal to 3. Okay, so we can assume it's 3. Oh, why can we assume it's 3? It might go past. Okay, that's fair. It could go past. Let me go back to the calculator quickly. It could go past. Let's check, I guess. Let's put x max, 100. All right, and let's just trace. It's kind of a question of faith at this point, because we're not really doing this with formal limits, and I'm not proving to you that it's equal to 3, but I'm getting 2.9996 at this point. And the closer I get, as I go to the right, it's just going up and up and up, but it's never, doesn't seem to be actually hitting 3. It's just getting closer and closer. And it's possible, by the way, it's not out of the question that the limit or the asymptote is actually at like 3.01 for all we know, but it doesn't look like it. It looks to me like it's going to 3. Maxima and minima. Okay, so this is another feature that your calculator is super, super well suited to doing. But if I have a curve that changes direction, changes in the y direction, then I'm going to have a local max and a local min. Now, I say local max and min because those are different from the global max and min. If I have a function that's only defined over a certain interval, the global min is the smallest value of the function takes anywhere. It's the smallest value in the range, and the maximum is the largest value in the range, the largest possible value. And a local max and a local min are basically turning points in the middle. And we'll talk about these more when we get to calculus, when we talk about stationary points. But for the moment, we can find these with our calculator using the max and min features. So as an example, if I had the function 3, that's x cubed, 3x cubed minus 2x, and I plotted it on the calculator, I would find a maximum at approximately -0.471, a comma 1.63, and a similar one on the other side, just by using the min feature. So we're going to go over an example of that. I want you to find, using your calculator, the coordinates of the local maxima and then the local minima. So I'm plotting x cubed minus 5x squared plus x minus 3. So x cubed minus 5x squared plus x minus 3. And I'm going to keep, that was the window I had from last time, so I'm going to do -10 to 10, and then maybe, yeah, -10 to 10 is a good place to start. Let's graph that. Okay, so my minimum is not in my window, so I'm just going to make the y min a little bit smaller. Let's do negative 20 or negative 20. That should be good. And now I can see my max and my min. So let's start by finding the max. I'm going to hit second and trace to go to calc. I'm going to select the maximum, which is option number 4. And this is similar to the 0. I need to give the calculator a left bound and then a right bound. And I'm just going to hit, I can put a guess if I want to, but I don't think I need to here. Yes, it's going to find a maximum at x is equal to 0.103 and y is equal to negative 2.95, negative 2.95 if I round that. Right, to find the minimum, same thing, except I go to the minimum option, scroll a little bit to the right, put a left bound here, and a right bound here. And yeah, so x is equal to 3.23 and y is equal to negative 18.2. So I think it might be worth just giving you quickly a sense of what the calculator is doing and why you need to give it a left bound and a right bound. You're essentially telling it where to search for the maximum and minimum. And what it's going to do is it's essentially going to pick values. It's going to start on one bound and compare the other bound. And it's going to decide, it's going to iterate going back and forth until it finds the minimum in that range. So let me go back to the question because we have found our max and min now. So we found a maximum at 1.03 and negative 2.95, 0.103, sorry. And we found a local min that was at 3.23 and negative 18.2. So that's option 3. Perfect. So that's all of the material from function graphs. I want to talk now about composite functions and inverse functions. And this, I think, is probably the most conceptually tricky part of the content in function theory. So we're going to take our time here and feel free to ask questions at any point. But composite functions are essentially nothing more than passing one function into the other. And we use this little circle symbol to say f compose g, which means take the output of g and put it into f, which means that f composed with g at x is nothing more than f of g of x. This formula is not in your booklet, but hopefully it's relatively intuitive to remember. Just focus on understanding the order. The x goes into g first, and then that all goes into f. So for example, if I have f of x is equal to x squared and g of x is equal to 2x minus 1, then I can find f of g of x by taking 2x minus 1 and putting it into f, replacing x with 2x minus 1. So I get 2x minus 1 squared. If I expand that, it's all of this. And going the other way, g of f means I take x squared and I put it into g. So I get 2x squared minus 1. So here's an example. Pretty similar to the last one. I want you to find f composed with g and g composed with f. I'll give you a minute. All right, let's start on part A. I'm doing f of g of x is equal to f of g of x, and g of x is 3 plus 2x. So it's f of 3 plus 2x. And f is x squared plus 2, so I need to square the input. So 3 plus 2x squared and subtract 2. The answer probably wants us to expand that, so it's going to become 4x squared. 3 times 2 is 6, and I have 2 of those, so plus 12x plus 9 minus 2. So that's going to be plus 7. That is option number 1. Sorry, plus 7, option number 2. And then g of f of x, we're going the other way. So we're doing 3 plus, let me just write, g of f of x is equal to 3 plus twice whatever f is, so x squared minus 2. So this is all equal to 2x squared minus 4 plus 3 is minus 1. And that is option number 1. Cool. Here's another slightly more difficult exercise, or at least trickier exercise. I'm going to give you a minute for this one as well. Okay, so let's take a look at this. I have f of x, which is a square root of some mess, and g of x is 5x minus 3, and I'm trying to find f of g of 1. So I don't actually need to find f of g of x, which is kind of nice, because it means I can just find g of 1 as a number and then plug that in, and I'm going to save a lot of algebra. So f of g of 1 is f of g of 1 like that, and that's equal to, let's start by finding g of 1. 5 times 1 minus 3 is 2, so then f of g of 1 is the same as f of 2. So I have 5x cubed. So I have a square root. 5x cubed is 40 plus 6 plus 3. That's the square root of 49. That's equal to 7. So option number 4. Next concept, the identity function. You're never going to see really a question that'll say the identity function on the exam. It's just useful to understand it, to put inverse functions in context. But the inverse function is the function I of x is equal to x. So whatever value you put in, the same value comes out. It's a function that does nothing. And it's useful to understand that because the inverse of a function f is the function f negative 1. We write it f to the power of negative 1. That cancels or undoes f, which means that if I do f negative 1 of f, I just get back x, which is the same thing as the identity function, right? And this is supposed to work both ways. So if I do f of f negative 1 or f negative 1 of f, it's the same thing because they're opposites of each other, and that's a relationship that works both ways. But that also means that f negative 1 is the inverse of f, again, because it works both ways. And that means that the inverse of the inverse is the original function. And that's something that could rarely show up in a question, but it's still a useful property to know. Now, not every function is going to have an inverse. At the standard level, when you're talking about inverse functions, you can always assume that the function is actually invertible. The sort of question will be designed in that way. We'll talk later at the higher level about the conditions under which a function is invertible and how we can find that condition and possibly restrict the domain. So if I take the, this is the formal definition of the inverse function. F negative 1 of f is just x. So here's a silly little example. If I do f composed with f negative 1 of 3, I'm just going to get back 3, essentially because f of f negative 1 cancels and just gives me back the same thing. All right. Finding the inverse of a specific value. So if I'm trying to find f negative 1 of 3, for example, in a certain function, I can, let's say that I call f negative 1 of that value x, and I take f of both sides. I get something like f of x is f of f negative 1 of b. But because f and f negative 1 are inverses, that just cancels to b. So essentially f of x is equal to b, and x is what I'm looking for. So that means that finding the inverse of a specific value is equivalent to solving the equation f of x is equal to b. So if I'm finding the inverse of the value b, I want to solve the equation f of x is equal to b. And if you think about this graphically, that basically means that finding the inverse of a value, f negative 1 of b, means that we're drawing a vertical line, a horizontal line at y is equal to b, and we're finding the x-coordinate where that intersects the function. And if you're asking the question, well, what if it intersects in 2 places? At the standard level, it can't, because if it did, it would not be an invertible function. But more on that later. So in this example, I have f of x is 3x plus 2, and I'm trying to find f negative 1 of 11. So if f of x is equal to 3x plus 2, and I'm trying to find the inverse of 11, I equate f of x to 11. So 3x plus 2 is 11. That means x is 3. So f negative 1 of 11 is 3. Okay, I'm going to give you guys 30 seconds to solve this question. This one should be pretty easy. Okay, so remember, finding f negative 1 of 3 is the same thing as solving f of x is equal to 3. So x cubed minus 5 is equal to 3. It means that x cubed is equal to 8, which means that x is equal to 2. Now, it's a pretty common mistake here. I've seen this far too often for students to say plus or minus because you're doing a cube root of both sides. You only do a plus minus if you're doing the square root or the fourth root or any even root, right? If I take negative 2 to the power of 3, I get negative 8. So the only solution to x cubed is equal to 8 is x is equal to 2. It's just sort of something to force to stick in your brain because it'd be really, really annoying to lose points on the exam for a mistake like that. So x equals 2 is my answer. So I'm trying to find f negative 1 composed with f negative 1 of 4. So first thing to do is realize that if I compose f negative 1 with f, all right, so these two functions, it's going to do nothing. It's going to cancel. It gives me the identity function. So really, I'm just looking for f negative 1 of 4. That's all I'm looking for. And f negative 1 of 4 means solving the equation f of x is equal to 4. And to do that on a graph, I'm thinking about a horizontal line at x is equal to 4, and I can at y is equal to 4, and I can draw that better. And I'm trying to find where it intersects. And I find x is equal to 6. So that is my answer. Now, the graphs of inverse functions. All right, so we said that the identity function was the function I is equal to x, which is a straight line with a slope of 1 passing through the origin. And we said that if I compose f and its inverse function, I get the identity function. But we can also think about the inverse function as essentially mapping the outputs of so if a function f maps inputs to outputs, the inverse function is going to map those inputs back to the inputs. And when we talked about the graph of a function f, we said that we're going to plot these points y is equal to on the curve of y is equal to f of x by making the x coordinates the inputs and the y coordinates the outputs. So if f negative 1 is doing the opposite, that essentially means I'm switching the coordinates. So I'm swapping x and y, and that's how I'm relating the outputs back to the inputs in this f negative 1 of x. So if the graph of f negative 1 of x is going to be essentially just swapping the coordinates of every point on the graph of y is equal to f of x, that means that the graph is going to be the mirror image of y is equal to f of x in the line y is equal to x. Because if I take, let's say I take 3, 1, which is about here, and I swap the x and y coordinates, I'm going to get 1, 3, which is approximately here. And you can see this kind of diagonal line that's showing you the direct map between the inputs and outputs and the outputs and inputs, essentially the relationship between the points and the corresponding point on the inverse function. So here's a little exercise. I want you to sketch the graph of f negative 1 of x. This, by the way, you just drag these points around, and once you get them in the right place, you hit grade, and it'll tell you if you got it right. I'll give you a minute for this as well. Okay, let's talk about the solution here. So basically, I'm going to have to rearrange these 3 points to correspond, like we said, to the fact that the inverse function is the mirror image of the original function. So I want to mirror this function in the line y is equal to x, which looks something like this. This is y is equal to x. So I need to mirror in that line, right? So any point that lies along that line, if you're on the mirror, it's not going anywhere. So this point I can just drag to there. Now the point negative 1, 3, if I switch the x and y coordinates, is going to become 3, minus 1. So that's just going to go here. And then the point 5, 4, if I swap x and y, becomes 4, 5. So that just goes there. If I hit grade, graph is correct. Perfect. Any questions about this? So the domain and the range of inverse functions. Like I said a second ago, you can think of the inverse function as taking the outputs of f back to the inputs, right? So that means that the things that go into the inverse function are the things that came out of the original function. That means that the domain of the inverse function, which is the things that can go in, is the range of the original function, and vice versa, because what comes out of the inverse function are those things that could have gone into the original function. So that's the domain of the original. So that means that the domain of f negative 1 is the range of f, and the range of f negative 1 is the domain of f. Now, just a note for higher level students, that's not 100% true if you have a domain restriction on f, right? You have to be a little bit careful when you restrict the domain when you're thinking about the range of the inverse or something like that. But for example, if I have f of x is equal to the square root of 4 minus x squared, find the domain and range of f negative 1. And I'm realizing now that this function doesn't have an inverse because it's symmetric, but it's okay. We can still answer the question in the context of what we have. So I know that this function f of x has a domain of -2 less than or equal to x less than or equal to 2, because the square root has to be, inside of the square root has to be positive, and that means the range of f is going to be f negative 1. And since the range of f is between 0 and 2, the domain of f negative 1 is between 0 and 2 inclusive. Now, one more time, just a reminder, This is not actually an invertible function. I should have picked a different function, but it does illustrate the concept nonetheless. And the same rules are going to apply. It's just not a good example. All right, so I'm going to give you guys a second to solve this question, maybe a minute. Okay, let's take a stab at this. The domain of f of x. What are the possible values of x that I can put into f? So the square root, that square root of x plus 2, is only defined if x plus 2 is positive. So x plus 2, I should say positive or 0. So x plus 2 is greater than or equal to 0. So x is greater than or equal to negative 2. Now that's the domain of f, which is going to be the range of the inverse function. So to find the domain of f negative 1, I need to find the range of f. So I'm just going to say this is the domain of f. And now the range of f is the possible values that can come out of f. So a square root is always positive, and I'm doing 4 minus square root. So that means the maximum value of f is 4. So I'm just going to put an upper bound of 4 for the moment. And then x plus 2, can be infinitely large. I can put a million x plus 2 and take the square root. So there's going to be no minimum, which means I can write this as negative infinity. I use my circular brace because you cannot include infinity. And that makes the range of f negative infinity to 4, which makes the domain of f negative 1 negative infinity to 4 as well. There we go. Part B, like we said, the domain of f was x greater than or equal to negative 2, which makes the range of f negative 1 that same thing. So negative 2 and bigger. So that's option 2. All right. Now we're going to talk about how you actually find the expression of an inverse function. So if I'm given the expression for f of x, how can I find f of x, or f negative 1 of x? So remember a second ago I was saying that the inverse function is the function that brings the outputs of f back to the inputs of f. So it reverses f. And when I have a function f of x, if I replace f of x with y for a second, and I have y is equal to something that depends on x, the x is the input and the y is the output. And when I'm looking for the inverse function, I'm basically trying to find what is the input that gave a certain output in the original function. So I'm looking for x given a specific y. And the way you have to do that algebraically is to rearrange your equation to get x in terms of y. So you want to isolate x. So let's look at an example here. If I have f of x is x minus 1 over x plus 2, then, and this is a common thing you can do to make it maybe a little bit more intuitive, is you swap x and y. So you replace x with y and y with x, and then you're going to isolate for y. So I swap and I get x is equal to y minus 1 over y plus 2. And then if I multiply both sides by y plus 2, I get this y plus x, yx plus 2x is equal to y minus 1. Now, if I factor out y, if I bring all the terms with y to the left-hand side and I factor it out, I'm going to get y times x minus 1. Let me just show you that maybe in one step. Let's do yx minus y is equal to negative 1 minus 2x. And I factor out my y, x minus 1 is equal to negative 1 minus 2x. And then all I do is I divide both sides by x minus 1, and I get negative 2x plus 1 over x minus 1. And that's the expression for f negative 1 of x. Now, if you don't swap the x and y, because you don't have to, you end up with an expression x equals something that has y's in it. And you just have to, at this point, at the end, swap x and y and write f negative 1 of x is equal to, and you replace all the y's with x. Let's do a quick example. I'm going to give you probably 2 minutes to do this one. It's a little bit harder. Let's go over the answer to this question. So like I said, the procedure for finding the inverse function, I start by writing y is equal to 3x minus 2 over x minus 1. And I prefer to swap the x and y at the beginning. So I write x is equal to 3y minus 2 over y minus 1. And now I'm going to try and isolate y. So how do I do that? I do multiply both sides by y minus 1, and I get yx minus x is equal to 3y minus 2. That means that if I factor out, if I bring all the y's to one side, I get yx minus 3y is equal to x minus 2. which is the same as y times x minus 3 is equal to x minus 2, which means that the answer is x minus 2 over x minus 3. That's f negative 1 of x. And that is option number 3. Good. So now we're ready for some harder exam style problems. We're going to do, I think we have 3 or 4 SL problems. Then we're going to cover the higher level material, and then we're going to do the higher level problem solving. Okay. So let's start with a relatively straightforward problem. I'm going to give you guys 5 minutes to try this on your own. It's much more valuable for you guys to give a real attempt than just to watch me solve it. So I'll give you a few minutes. Okay, so let's go over this. You guys can keep working if you're finishing up part C. I'm going to start from the top though. So I'm trying to find f negative 1 of 5. And remember that finding the inverse of a certain value is the same as solving f of x is equal to 5. So 3 plus 2x is equal to 5. That means that 2x is equal to 2, or in other words, x is equal to 1. Okay, x is equal to 1. Part B, I'm trying to solve the equation g of f of x is equal to 9. So g of f of x is equal to, I'm going to plug f into g to find the expression for g of f of x. So I'm going to take 3 plus 2x and put it into g. So that's going to be negative 3 plus 2x squared. And that's supposed to be equal to negative 9, which means that 3 plus 2x is equal to 9. And sorry, there's supposed to be a square here. That means if I take the square root of both sides and I put a plus minus, 3 plus 2x is equal to plus or minus 3. So plus or minus 3 minus 3 is either 0 or minus 6. So my answers are x is equal to 0 or minus 3. See multiple choice options. So I have 0 and minus 3. There we go. And now in part C, we're trying to find the value of x satisfying f negative 1 circ g composed with g of x is equal to negative 7 over 2. So what I'm going to do actually is the easier way to find this, instead of finding f of x, f negative 1 of x, is to take f of both sides. So I'm going to do f of f negative 1 of g of x is equal to f of negative 7 over 2. And I do that because f and f negative 1 are going to cancel. And that means that I'm left with just g of x is equal to, and I find f of negative 7 over 2 by plugging negative 7 over 2 into the expression 3 plus 2x. So 3 plus 2 times negative 7 over 2 is negative 7. That's minus 4. And g of x, remember, is negative x squared, which means that x squared is equal to 4. So x is equal to plus or minus 2. And those are my answers. Let's check. Plus or minus 2. There we go. So I have drawn the graph of f in this diagram, and I want you to start by finding the domain and range, and then f of minus 4, f negative 1 of minus 1, and y is equal to f negative 1 of x. So I'm going to give you guys 2 minutes to get started and get a bit of a head start on me, and then I will continue. All right, so domain and range of f. I see on the graph that the possible x values that are in the domain are everything from negative 11 inclusive up to 5 inclusive. So my domain is negative 11 less than or equal to x less than or equal to 5. And the range is, well, the minimum value is minus 2, and the maximum value is 2. So negative 2 less than or equal to f of x less than or equal to 2 is the range. So my domain is from negative 11 to 5, and the range is from minus 2 to 2. Now to find, in part BI, f of minus 4. I start by finding f of minus 4. And f of minus 4, I go to x is equal to minus 4, I find the value of y is equal to 1, so f of minus 4 is equal to 1. And I plug that back in again to f because I'm composing it. So then I go to 1, and I find the y value there, and that is 0. So f of 1 is 0. That means that f of minus 4 is equal to 0. And there's no multiple choice there. I must have forgotten to make it. Now, f negative 1 of minus 1. All right, so remember that finding the inverse at a certain value is the same thing as solving f of x is equal to that value. So in this case, f of x is equal to minus 1, which we can consider as drawing a vertical line at y is equal to, I keep saying vertical line, it's a horizontal line at y is equal to minus 1 that intersects the graph, and that's the value that we're looking for. And we notice here that it intersects at x is equal to 4. So that's the answer. So this is 0, and this is 4. I'm just writing them down because there's no multiple choice. For these, you can always type in your answer. So if you do 0 and 4, you can get graded, even if there's no multiple choice. All right, and now, part C, we're trying to sketch the graph of y is equal to f negative 1 of x. Now, in this question, I'm kind of being nice and I'm giving you this draggable drawing that's a little bit easier than drawing it out from scratch. But when you do draw this, you have to remember that I am drawing a straight line, or I'm drawing the reflection, the mirror image of the original function in the line y is equal to x. So that's the mirror image. And I'm going to start by mirroring each of the points. So I have this point 5 comma minus 2, which becomes minus 2 comma 5. So that's going to go over here. This point negative 11 comma 2 is going to become 2 comma negative 11. So that's going to be over here. And then I have the points that I found in B. So I have 1 comma 0 becomes 0 comma 1. That's going to be there. And the shape is going to be more or less the same. So I'm going to try my best to trace this like that. And you're going to have something that looks roughly like that. Now on this diagram, I'm just going to drag this endpoint to, that's supposed to be 2, negative 2 comma 5, so one more up. I'm going to drag this to 1 comma 0, and this was at negative 11 comma 2. Let's grade that. Boom, very good. Nice. Okay, let's move on to a slightly harder problem again. So I have a function that's defined by f of x is the root of 5 minus 3x. And we're first trying to find an expression for f negative 1 of x, okay? So the procedure is the same. I swap x and y, and I say x is equal to the square root of 5 minus 3y. And I'm trying to isolate y. So I'm going to square both sides. X squared is equal to 5 minus 3y. And I'm going to isolate the 3y, bring it to the left, and bring the x squared to the other side. So 3y is equal to 5 minus x squared, which means that f negative 1 of x is equal to 5 minus x squared over 3. Let's check our multiple choice options. 5 minus x squared over 3. Let's talk about part B, I. So I'm thinking about the domain of G composed with F composed with G. So it's a triply composed function. All right. Now you can simplify this slightly. There's a a more traditional way to do this, but you can make this a little bit easier by recognizing that G is 1 minus X has a domain of all real numbers. Anything can go into G, which means whatever the domain of F of G is going to be the domain of F of G of F of G, because the G is not going to change the domain. It's all possible values. So I just want to find f of g of x and think about its domain. So let's do that. F of g of x is the square root of 5 minus 3 times, and I plug in now g, 1 minus x. So this becomes the square root of 2 plus x. And I need to think about what the domain, sorry, that's supposed to be 2 plus 3x. Think about the domain of this. So right, this inside of the square root has to be positive. That means that 3x plus 2 is greater than or equal to 0. So x is greater than or equal to minus 2 over 3. And that should be the answer. Greater than or equal to. no, greater than or equal to. There we go. All right, let's talk about BII now. So I found in part A that f negative 1 of x was, just going to double check, it was 5 minus x squared over 3. 5 minus x squared over 3. And now I'm composing f negative 1 of g, which means I'm putting g into f negative 1, which means f negative 1 of g of x, I replace x in my expression for f negative 1 with the expression for g, which is 1 minus x. So 5 minus 1 minus x all squared, and I divide that by 3. So if I expand the numerator, I'm going to get, and actually we don't need to expand that. We can just think about the range. I'm going to take out 5 over 3, and I'm going to do minus 1 over 3, 1 minus x squared, right? So I have a constant, 5 over 3, minus 1/3 of some square number. And a square is always, the square of a number is always going to be positive. So I'm doing 5 over 3 minus any positive number. And because those numbers are positive, I know that the maximum value here is 5 over 3. Now I need to think about the minimum value by thinking about what the domain of f negative 1 is. What are the possible values that I can put in? And in this case, it looks like it's any values of x, but actually you have to be a little bit careful because not every value of x could have come out of f of x. So notably, the range of f is only positive numbers. So it's f of x greater than or equal to 0, which means that the domain of f negative 1 of x is also x greater than or equal to 0. So domain f negative 1 is x greater than or equal to 0. And that means that the g of x has to be, the thing I'm putting into f negative 1, g of x has to be bigger than 1 minus x. No, g of x is equal to 1 minus x, and it has to be greater than or equal to 0. So 1 minus x greater than or equal to 0, which means that x is less than or equal to 1. And I was just double checking, but that is actually, if we plug in 1 into here, we're gonna get 0. And as we go negative, this term can take on any value. So there's going to be no minimum, and the answer is negative infinity up to 5 over 3. Let's check the multiple choice options. Negative infinity, inclusive, sorry, not inclusive, and 5 over 3 is inclusive. There we go. Okay, so we're going to move on now to the higher level only content. We have a little bit more theory to cover, and then we're going to do a bunch of problems. The first thing we're going to talk about is even functions. So an even function is one for which f of negative x is equal to f of x, which basically means that the function is symmetric about the y-axis, right? The y-axis is the mirror line for the function. You can see that in this picture. Every point on the graph has a mirror image that's directly across the y-axis from. Similarly, odd functions, f of negative x is equal to negative f of x. So now we're not mirroring in the y-axis, we're actually mirroring at the origin. So each point doesn't just flip to the other side of x, it also flips to the other side of y. And you can see that graphically if you take a point and graph it to its corresponding point, they are all going to pass through the origin. So I'm going to give you guys a second or maybe 2 minutes to try this exercise. For what value of k is the function even, and for what value of k is the function odd? So I know that a function is going to be even when f of negative x is equal to f of x. So if I write f of negative x out, f of negative x is equal to, fraction here, x squared, negative x squared is just x squared, so that doesn't change. Same in the numerator, k plus 1 x squared plus 3k minus 5, and this time this is negative x. All right, so that's the difference. And if this is an even function, that means that this is equal to the original, which is the same thing, so k plus 1 x squared plus 3k minus 5 x over x squared plus 1. And if I ignore the denominators because they're not going to be 0 and there's no issue there, and then I can cancel out k plus 1x squared, I'm left with negative 3k minus 5x is equal to 3k minus 5x. And that tells me that this has to be true, by the way, for all x, not just for one specific x. So it can't just be x is 0. That means that 3k minus 5 has to be equal to 0 because the number is only equal to its negative if that number is 0. So 3k minus 5 is 0. That means that k is equal to 5 over 3. All right, now the function is going to be odd when f of negative x is equal to negative the original function. Okay, I can do the same thing before. The denominators aren't going to matter because they're the same. And then I'm left with k plus 1 x squared plus, or in this case, sorry, minus 3k minus 5x, because I take the negative and put it in front, is equal to negative k plus 1 x squared minus, again, this minus distributes with that plus, minus 3k minus 5x. So on both sides, I have negative 3k minus 5x, so I can cancel those. And then I'm left with k plus 1 x squared is equal to negative k plus 1 x squared. And just as in the previous part, this is true for all x, which means that k plus 1 has to be 0 because I have a number equal to its negative. I didn't put a multiple choice option, that's my bad, but the answer is k is equal to minus 1. I want to talk about the existence of inverse functions. When do they exist? So we know that a function has to pass the vertical line test. Each input has to go to at most one output. And since f negative 1 has to also be a function, it must pass the vertical line test. But we know that the graph of f negative 1 is the mirror image, it's the reflection of the graph of f of x in the line y is equal to x. And that means that the graph of f of x must pass a horizontal line test for its inverse to exist. Let's open this up and take a closer look. If, let's say that I had an inverse function, or a function that didn't pass the horizontal line test, and I reflected it in the line y is equal to x, then that new curve would not pass the vertical line test. And that would not be a valid function, which would mean the inverse function does not exist. And you can think about this alternatively as imagining that if I have a function that takes two different numbers, let's say 1 and 3, both go to the same output, then the inverse function, if you give it that output, it can't possibly know whether it came from 1 or from 3. So the inverse function is not well defined. And just worth mentioning, the way we address this this issue when we have problems is that we have to restrict the domain of the function such that it passes the horizontal line test. And that basically means that there is no maxima, no local max or local min in the function at all. So we were talking earlier about a quadratic, and we were restricting it at the vertex because we can't go past any maximum or minimum. Now, self-inverse functions, this one is, officially it's in the syllabus. I've never actually seen it show up on the exams in the new syllabus, but it could happen, so you sort of have to be prepared or at least know what it means. And a self-inverse function is a function that when composed with itself, it's its own inverse, so you compose it with itself and you get the identity function x. And since the graph of f negative 1 of x is the mirror image in the line y is equal to x, and the function has to be, we're saying it's its own inverse, that means that the function f, if it's self-inverse, has to be symmetric in the line y is equal to x, because I reflect it to get the inverse, and it's the same function, means that the reflection can't change anything. That's only possible if it's symmetric in the line y is equal to x. So, for example, the function 1 minus x is self-inverse, because if I do f of x, that's 1 minus x is just x. So here's an example for you to do. I want you to find the value of k such that this function is self-inverse. I'll give you a minute. So if a function is self-inverse, it means that if I compose it with itself, I get back x. So if I do f of f of x, I should just get x. So let's actually compute f of x. So if I plug k plus 1 x plus 2 as x back into f, so I'm going to do f of k plus 1 x plus 2, I'm going to get k plus 1, and then I'm replacing x with k plus 1 x plus 2, and I'm adding 2. That's supposed to be equal to x. So let's expand it, and I have k plus 1 squared times x plus 2 times k plus 1 is 2k plus 2. And I add 2, that's plus 2k plus 4 is supposed to be equal to x. Okay, so that means that I want k plus 1 squared to be equals to 1, because I have 1x on the right-hand side, and I want 2k plus 4 to be equal to 0. All right, so this means that k plus 1 is equal to plus or minus 1, which means that either k is equal to 0 or k is equal to minus 2. If k is 0, and I plug it in here, that does not work, because I get 2 times 0 plus 4 is 4, and not 0. But if I put k as minus 2, I get 2 times minus 2 plus 4 is 0. So the answer is k is equal to minus 2. Finding the inverse with domain restriction. So when a function is not one-to-one, that means it doesn't pass the horizontal line test, its domain needs to be restricted for the inverse to exist. So, for example, if I have x minus 1 all squared plus 2, then, and I let g of x equals to f of x for x is greater than or equal to a. So we usually define a second function that has the restricted domain. And we want to find the smallest value of a such that g negative 1 exists. X is greater than a, so we're looking to the right. So basically, we're looking for the vertex of this quadratic, because if we went past the vertex in our domain, then there would be some value to the left of the vertex that has the same y-coordinate as some value to the right of the vertex, and that would violate the horizontal line test. So we find a vertex at 1, 2, which means we need to cut the function there so that the inverse exists. So we want x to be greater than or equal to 1, so a is equal to 1 in this example. It's worth mentioning that on exams, one of the ways this is often tested is in combination with calculus, because it's not always going to be a quadratic. It won't be so easy to find the minimum or the maximum. You're going to need to use calculus to find the stationary points and then restrict the domain. It also sometimes shows up as a calculator question where you find the coordinates of the maximum and minimum using your calculator, and then you restrict the domain to being between those 2 points. So different ways it can show up, but as long as you understand the idea of stationary points, maxima, local max and local minima being the problem, things that we cannot include in the domain except at the endpoints, you'll be able to solve any of those problems. So here's an example. I have the function 2x squared plus 6x minus 8 is defined on the domain x less than or equal to a. And I want you to find the largest possible value of a such that the inverse function exists. I'll give you a minute. All right, so this is a quadratic function. And I know that a quadratic function looks like a parabola, and it's going to have a vertex. And the vertex is where I need to cut the function. So a is the x-coordinate of the vertex. This is a concave parabola, so it looks something like this. And we're saying x is less than a, so we're looking for this entire branch. Because otherwise, if I included anything more than that, we would fail the horizontal line test. So to find the vertex of a quadratic, I'm only looking for the x-coordinate. I don't actually need the y-coordinate. I can use x is equal to negative b over 2a, or in this case, negative 6 over 2 times 2. That's negative 6 over 4 is negative 3 over 2. That's option number 2. All right, now we're going to get started on the higher level problems. So I'm going to give you guys 5 minutes to solve this first question, or at least get started, and then I'm going to explain how to do it. All right, let's go over the solution to this problem. I have a function f of x is equal to 8 over x squared minus 16. And in part A, I'm trying to determine whether f is even, odd, or neither. So I can tell by looking at this that the only dependence on x is x squared, which means whatever I plug in negative x, it's going to become squared and it's not going to make a difference. But it's important to show your working when you're answering this question on the exam. So I'm going to write f of negative x is equal to 8 over negative x squared minus 16, which is equal to 8 over x squared minus 16. So f is even. All right. Even. Part B, sketch the graph of y is equal to f of x, labeling any axes, intercepts, asymptotes, maxima, or minima. Okay, so let's think first about x squared minus 16, which is a concave up parabola that has a minimum at negative 16. So let's just draw that better than that, actually. Let's do coordinate axes, and then x squared is going to be, or x squared minus 16 is something like this. Sorry, that should be not a straight line. It should be like this. And it's going to have roots at negative 4 and 4. And I'm going to be doing 8 divided by that. And we haven't talked about function transformations yet, but we'll give you a brief overview now. When the denominator is 0, I'm going to have a vertical asymptote. So I can already draw vertical asymptotes here. I know that the function is going to sort of approach those values. I also know that because the numerator is positive and the denominator is positive up here, it's going to be positive over here, and it's going to be positive over here. Now, between the two roots, and maybe let me just draw that in a different color. The function is going to be positive over here and positive over here. Between the two roots, it's going to be negative, and the question is how much? So if this is negative 16, then when I do 8 divided by that, that's the minimum, 8 divided by negative 16 is negative 1 over 2. So I'm going to go through here, negative 1 over 2. And I know that anywhere between the roots, the denominator is negative, so the whole function is going to be negative. So I'm going to have something that looks like this. I can draw that better. It should be symmetric at the x-axis, like that. That's my answer. Now, we have a function, g, which is defined as g of x is equal to f of x, but it has its domain restricted. So we have x greater than or equal to 0, and we want to find an expression for g negative 1 of x. All right, so I have 8. Let me start by replacing x, or swapping x and y. So x is equal to 8 over y squared minus 16, which means that y squared minus 16 is equal to 8 over x. That means that y squared is equal to 8 over x plus 16, which makes y equal to the square root, and we got to put plus or minus for the moment, and we'll decide in a second, 8 over x plus 16. And now we said that the domain of g is x greater than or equal to 0, which means that the range of the inverse function, g negative 1, is going to be y greater than or equal to 0, which means we need to have positive. So g negative 1 of x is equal to the square root of 8 over x plus 16. And let's look at the multiple choice answers. It's putting it over a common denominator. If I put 16 over x, it's 8 plus 16x over x. And that's that option. Yep, perfect. And finally, find the domain of g negative 1. So the domain of g negative 1 is going to be the range of g. And to do that, it's going to be helpful to go back to the, well, actually, I erased the graph, but I'll redraw it quickly for you. We had drawn a graph that looked roughly like this. This was negative 4 and 4. And it was passing through 1 over 2 here. it was a maximum there. So I'm going to try and draw it a little bit better. There we go. -1/2. Okay, so the range of the function, remember, we cut it off here, and we are considering only the part that's positive for g of x. So g of x is something like this. And basically, we notice that g of x can take on any value except for any values between here and here. It can't be anywhere between 0 and -1/2. We just got to be careful with our inclusive signs. We know, because we have an asymptote of y is equal to 0, that y is greater than 0 is one of the intervals, and the other interval is y less than or equal to -1/2. So if I merge those and I write them in interval notation, I have -∞ up to -1/2 union, and sorry, this 1/2 is inclusive, so square bracket, union 0 exclusive up to infinity exclusive. Let's see our multiple choice answers. So x is less than or equal to 1/2 or greater than 0. There we go. Moving on to the next question. Yeah. So I'm going to give you a moment to do this on your own, and then we'll go over it. So I f of x is the square root of -x² plus 4x plus 5. And I'm going to find the domain by remembering that the inside of the square root cannot be negative. So -x² plus 4x plus 5 is greater than or equal to 0. And I'm going to multiply both sides by -1, x² minus 4x minus 5, and I switch the direction of the inequality, which you have to do when you multiply by a negative number. And I'm going to factor this, so I'll do x squared plus x minus 5x minus 5 is less than or equal to 0. So this is x times x plus 1 minus 5 times x plus 1, x minus 5, x plus 1 is less than or equal to 0. What does this look like? This is a root at 5 and -1, and I have a concave up quadratic, -1 and 5. I'm looking for where it's less than 0, so between the two roots. So I want x greater than or equal to -1 and less than or equal to 5. Let's check. So from -1 to 5 inclusive. Nice. And now the range of f, I'm just going to erase this. The range of f is the possible values that the function could output. So I know that the square root is always going to be positive or 0, so the minimum value is going to be 0. And the maximum value, I have to think about the maximum value of the inside of the square root, okay? So we found a second ago that we had roots at -1 and 5, which means that the x-coordinate of the vertex is at halfway between the two, so 5 plus 5 minus 1, it's at 2. We can also do -b/2a. It's going to give you the same thing. And f of 2 is equal to the square root -4 plus 8 plus 5 is equal to √9, and that is 3. Okay, so that means that my range is from 0 to 3 inclusive. So I would write 0,3 and submit that for grading. Nice. So now we have a second function h, which is h of x is equal to f of x, except that we've restricted the domain to x less than a. And again, we're restricting the domain so that we pass the horizontal line test. And we therefore want the a to be at the vertex so that we maximize the domain that we have. So x is less than a, and we're looking for the x-coordinate of the vertex, and we already found that that was at x is equal to 2. So that means a is 2. Okay. And now finally, find h-1 of x. So I'm going to start by swapping my x and y. X is equal to the square root, the square root of negative y squared plus 4y plus 5. I square both sides to get rid of the square root. X squared is equal to negative y squared plus 4y plus 5. Bring everything to the left-hand side, and I get y squared minus 4y plus x squared minus 5 is equal to 0. And this is a quadratic in y. Remember, I'm trying to isolate for y. So I'm going to say y is equal to negative b is, in this case, negative 4. So 4 plus or minus the square root of b squared is 16 minus 4 times a is 1, so just x squared minus 5. And all that over 2. So this is the same thing as 2 plus or minus the square root of 16. 16 minus 4 times minus 5 is 20. So that's going to be 36 minus 4x squared. minus 4x squared over 2. And I can factor out 4 from 36 and 4 to rewrite and pull out, and that becomes a 2 outside the square root. And that becomes 2 plus or minus the root of 9 minus x squared. And now the question is it plus or is it minus? Well, we said that h of x is defined for x less than a, and a we said was 2, so x is supposed to be less than 2. The output of the inverse function should be less than 2, so we want minus. So my final answer is h negative 1 of x is equal to 2 minus the square root of 9 minus x squared. So, yeah. Perfect. All right, so I have an odd function f and an odd function g, and I know that g negative 1 exists. And I want you to show that g negative 1 of f of x is odd. I'll give you a few minutes to try this one. It's pretty tricky, and then we'll go over it. Okay, so I'm going to show you how to do this. I want to show that g negative 1 of f is odd, which means I want to show, this is what I want to show, that g negative 1 of f of negative x is equal to negative g negative 1 of f of x. Okay, that's what I want to show. So I'm going to start by remembering that if g is odd, that means that g of negative x is equal to negative g of x, since g is odd. Okay, and now what I'm going to do is I'm going to substitute in for x. I'm going to say x is equal to g negative 1 of x. Or I'm not really going to say that x is that, but I'm going to plug that into the expression above. So g of negative g minus 1 of x is equal to negative g of g minus 1 of x. All right, so I substitute that in, and I know that on the right-hand side, I have g of g minus 1. This is just going to simplify to give me x. Okay, and now if I take g minus 1 on both sides, again, I know this is a little confusing, but if I take g minus 1 of g minus 1 of x, I'm going to get g minus 1 of x over here, and there was a negative here, right here. Or, sorry, the negative is here, g minus 1 of x. And these g minus 1 and g are going to cancel, and I get, that's supposed to be a negative x also. Negative g minus 1 of x is equal to g minus 1 of negative x. Okay, so that tells me that g minus 1 is odd, right? And now I can consider that g negative 1 of f of negative x, which is the thing I want to consider, I can write that as g negative 1 of negative f of x, because I know that f of x is odd, so f of negative x is going to be negative f of x. And I figured out that g was odd, which means that g negative 1 of negative something is negative g negative 1 of f of something. Okay? Which means I have shown what I wanted to show, that if I take g negative 1 and compose it with f and plug in negative x, I get negative what I wanted. So that means that g negative 1 of f of minus x is equal to negative g minus 1 of f of x. Okay, I know that's a little confusing. And also that there's no multiple choice for questions like these. I'm going to let you guys ask any questions that you might have while I show you how you can grade your work when it's a show that question or a question where you have to show your reasoning. So I'm just going to take a screenshot of my work. You can do this on paper. You can also upload from your phone. If you hit this scan your work, I'm just going to select images from my computer. And I'm going to select these two screenshots. I'm going to clear my screen also. My work is going to be transcribed. And then I can hit grade. So it wasn't completely happy with my work. You correctly demonstrated that g is odd, and you just have to show that g negative 1 is odd. Remember that for an odd function, what did I write? So negative, okay, I showed that, and then there is equal to g negative 1 of f of x. Well, that's not what I said. It misread my handwriting slightly, but yeah, I can fix the mistake by just plugging in that. Oh, it was that. And g negative 1 of negative x, and that comes out, yeah, and that should be good. Perfect, 5 out of 5. So the nice thing about this being transcribed and not just directly graded is that if it incorrectly read your handwriting and you need to fix something before you submit it for grading, you can do that, and you can see that it makes a difference, and it'll actually grade your question accurately. So let's do the last question. This is like a challenge question. And we're trying to find the value of k for which g of x is self-inverse. So I'm going to give you a couple minutes to get started on that, at least to sort of think about what you would do, and then we'll go through the process together because it is a little bit messy. All right, so we're trying to find the value of k for which the function g of x is equal to 2x plus 3 over x minus k is self-inverse. And a function being self-inverse means that it is its own inverse function. That is, that if I compose it with itself, I get the identity function x. So if I plug g back into g, I should just get back the same thing, x. So in other words, g composed with g of x is equal to x. And algebraically, that looks like g of, and I plug in for g the entire expression, 2x plus 3 x minus k, and that is supposed to be equal to x, right? Because the inside there is the output of g of x, and if I put that back into g, I should get back the input x. So what I'm going to do is I'm going to write out what g of 2x plus 3 over x minus k actually equals to. So we're going to need a big fraction, and then I'm going to replace 2x with twice the expression for g of x, so 2x plus 3 over x minus k plus 3. And I replace the x in the denominator with 2x plus 3, 2x plus 3 over x minus k. And that should be equal to x. Now it's a bit of a mess because I have a fraction in the numerator and a fraction in the denominator, but I can clear it a little bit by multiplying the top and the bottom by x minus k. So I'm going to multiply x minus k over x minus k. And that's the same thing as multiplying by 1, so I am allowed to do that without making any changes to the right-hand side. When I do that, the x minus k is going to cancel with the first x minus k in this denominator. So I'm going to get 2 times 2x plus 3, and it's going to multiply the plus 3. So plus 3 times x minus k. And that's all going to be over 2x plus 3, and the same thing, the x minus k is going to cancel there, minus k times x minus k is supposed to be equal to x. Okay, so if I write out the entire numerator and try and simplify as much as I can, I'm going to get twice. 2 times 2x is 4x, and I get another 3x from the second brackets, so that's going to be 7x. And then I'm going to have 2 times 3 plus 3 times minus k. That's going to give me negative 3k. So 7x, and let's not forget that 2 times 3 is plus 6 minus 3k. In the denominator, I'm going to have, if I collect all the x terms, 2x and then minus kx. So 2 minus kx plus 3, and then negative k times negative k is plus k squared. That's still equal to x. And now what I can do is multiply both sides through by the denominator to clear it out, and I'm left with 7x plus 6 minus 3k is equal to 2 minus k, and then x times x is x squared, plus 3 plus k squared x, like that. And now we're going to have to think about the two sides of the equation. I have one side where I have 7x plus 6 minus 3k, so I have a linear term, power 1x, plus a constant term. And then on the right-hand side, I have a term that's quadratic in x, so power 2, 2 minus k x squared, and a term that's linear in x. And because this equation has to hold true for all x, because it's a self-inverse function and not just self-inverse for a specific value, I know that the left-hand side has no x squared term, so the right-hand side also actually can't have an x squared term, which tells me that 2 minus k is equal to 0. In a similar way, on the right-hand side, I don't have a constant term, and on the left-hand side, I have a constant term of 6 minus 3k, and those also have to be equal, which tells me that 6 minus 3k is also 0. Now, thankfully, these two conditions are actually the same. One of them is just multiplied by 3 compared to the other, so if one is true, the other is also going to be true. And I'm just left with k is equal to 2 as my answer. Let's check that against the multiple choice. K equals 2 is the answer. Nice. Okay, so that was the last problem. Okay, I think we're going to call it then. Thank you very much for coming.